scheduling algorithm, including first come first serve and shortest job first, because sometimes the longer job hide the shorter job. What if the shorter job is important? So because of that, we have the longer waiting time. To address that problem, we have the shortest job first. Not only just the shortest job, we have the shortest remainder job first. Also, we can consider preemptive version and the non-preemptive version. Preemptive version, it can be resumable later. On the other hand, the non-preemptive, once it started, then it should be completed. So also we consider the priority-based scheduling algorithm. The lower number of the priority is the highest priority, and then will be selected by the scheduler. Okay, actually in both of you, almost all the scheduling algorithms are based on the priority. So, but depends on what is the priority. So first come first serve is the arrival time is the priority, and shortest job first is the amount of the CPU burst time is the priority, and the shortest remainder job is the same. So we can consider almost all the scheduling algorithm as the priority-based algorithm. To simulate such an algorithm, there are a bunch of the simulators. Okay, we can see. In later, we will see how to implement such an operating system algorithm. There are a bunch of different ways to implement the operating system algorithm. One way is you can develop the new operating system algorithm. And you apply your own algorithm to the new operating system, which is not easy, definitely. Then you can use some existing kernel operating system. Then by adding or replacing with your new algorithm, you can rebuild your kernel, which is popular. Also, that requires some rebuilding the kernel algorithm. Another way to implement and testing your operating system algorithm is a simulator. So this is an example of the simulator for CPU scheduler. So, for example, we will create the process state, which means the process name, and arrival time, CPU burst time. Sometimes if needed, it has a priority. Okay, then so we can select the algorithm first. We will select the first come first serve algorithm speed because it's a quickly move. So you can stretch out the time. For example, 30 process will be it's a time unit kind of the time unit. We will use 30 FPS. It's just nothing but the speed of your algorithm to animate. Okay. So let's test with the first come first serve. We need to show what is the next. This is the randomly created CPU number as well as the CPU burst time. So if you run the first come first serve, it will be processed. The first come first serve. The left hand side is a ready queue. The first left hand side is the first come, and the right hand side is later coming. So it's processed by the arrival time. Also, you can see
what difference between a red and the blue?
A red is in the
Executed.
executed. Okay, which means among the process state is the running queue, and the blue is in the ready queue.
Okay.
The white one is not created for your visualization, it shows. Okay? So this is a simulator. So also more important thing is you can see the performance of this algorithm. Like you can see the total CPU time and what is the average response time. Response time is 0 as soon as it will be created. And turnaround, how many processes will be processed and what is the waiting time, so on. What if we learn shortest the job first, and you see the shortest job will be processed. It's a different order, right? The red one is select the shortest job first. Okay. Among the blue color is in the ready queue. White one is not created yet. Okay, don't pay attention too much. Okay, among the blue color, shortest job will be selected. Then you can see it has the different turnaround time. The turnaround time is the shorter than the first come first serve. What about the priority? It's already done. So let's be quick. You can also select a preemption or non-preemption of that. Unfortunately, here we cannot see the priority. This is the priority. The bottom line is the priority. You can see. So 2 will be selected. You can see because it's a lower number. It's a higher priority, and so on. So this is the simulator. So if you can find from the internet bunch of such a simulator to understand the algorithm of the CPU scheduling algorithm. So today we are going to start with round robin. The round robin is the first. Even though we try to be fair with the processes in the ready queue, it's not perfect depending on the size, amount of the CPU burst time, and the priority. It's not fair. So what is a fairness? So to be fair with equally to the among the processes, instead of processing the remainder job or the size of the CPU burst time. So why don't we So we have the CPU time. Okay, we had the process 1, process 2, process 3. Process 1 need, for example, 10 CPU burst time. Process 2 need 8 CPU burst time. Process 3 need 4 CPU burst time. So we are going to segment the CPU time by certain period of time for, let's say, the 2 time unit. It can be 2 milliseconds, it can be 20 milliseconds, it doesn't matter. Okay? It depends on your algorithm. So let's say 2 time unit. Then allocate, segment each process by such a time unit, which is called the quantum, time quantum. So time quantum size is 2. So it's a 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Then we can use round robin. So P1, P2, P3. And P1, P2, P3. P1, P2, and P1, P2, P1. That's like it. This is the round robin scheduling algorithm. Very simple and fair.
In that case, arrival time is the quantum time.
Which one?
Arrival time is the
Arrival
quantum
time. If suppose that right now P1, P2, P3 are in the ready queue, then you can consider the process in the ready queue. For example, in the middle of a process this time, another process arrived. This one is already processed. Then if P4 is arrived with 10/6 and divide by time quantum, then this one will be processed, this one, then this one, this one, this one, this one, such a way. So arrival time doesn't matter. Okay? As long as process are in the ready queue, you can divide the processor CPU burst time by the time quantum and the assign. So advantage. What is the main advantage of this one? Fair. The more important thing is very quick response time. So no matter what size of CPU burst time, no matter what priority you have, it will be response at most 1 round. Okay? So it's on average. It's very fast response time. But it's very hard to say whether this is really fair. Fairness means we do not consider any priority. Okay? What if one of them has a very high priority, should be processed, but because of the fairness, uniform fairness, it cannot get the full CPU burst time. So anyway, overall, it's a fair. The problem, what will be the problem of this one? It has a lot of context switch depending on the size of quantum. So it's very important to find optimized time quantum. Okay? So in case, extreme case, time quantum is the too large, it's almost infinite, 2 hours, for example. That is the same as what? It's a first come, first serve. Because time quantum size is big enough to process any process. So it will be based on arrival time. So in case the time quantum size Q is large, it's the same as P4. If too small, okay, it's very good for waiting time, less waiting time, but it will cause a lot of overhead. Even though we do not consider overhead of the latency, dispatcher latency, in other words, the context switch over time, but it will cause such a problem. So you need to find such a optimized. Okay. But in this case, there are 2 different versions. First one is we need to segment CPU time by the time quantum allocate. Okay? What if in case you have the 1 remainder time? Okay? We can use only half of that. The other half is waste. To address that problem, in case the process is terminated and restart the time quantum for CPU time. So which means in this case we have the 20 time quantum. So process 1 is processed. So right now, this is the current status of the ready queue. So we have a full process. Process 1 has a 53 CPU burst time, process 2, 17, and so on. So next one is the P process 2, even though we process 2 get the 20 time swap, but because of the size of the CPU burst time, it will get only 17. Then from here, it's a 20 will be allocated for the next one. Okay? So we will use such a preemptive version of the round robin. So it's a guarantee, but I cannot say that it's really fair. It depends on. Sometimes if you consider the priority, you need to consider that. Anyway, it has a bounded waiting time, also very quick average response time. Okay, problem is if we wait, so it is hard to find optimize the queue. So to address that problem, we will consider multi-level queue. The next one is multi-level queue. Don't be confused. Even though we consider multi-level queue, that doesn't mean we have the multi-processor. We consider only the single processor. We will consider the multi-core or the the processor cases later. But here we have only one process. Okay. However, in the ready queue so far, how many ready queue we consider? Only one ready queue. This time we consider 2 ready queue. This is the ready queue, but when a process enters the ready queue, there are multiple ready queue. Suppose that we have foreground ready queue and background ready queue. We can classify the processes running on the operating system 2 types. One is a foreground, another one is background. For example, if you run your application program, it's a foreground processes. On the other hand, if you have printer server, do you need every time printer server process? No, only when you just submit a job, printer job to print out the document. At the time, printer server will be activated. But still need to wait until somebody submit the job. So it can be run as a background. Most of the service program is running on the background, or sometimes a batch job. You want to process the all student GPA calculation. It can be run as a background. It doesn't require very quick response time. Okay, but throughput should be good enough. So at the time, we can classify the process type by the foreground and background. The foreground, we can, for example, use round robin. Why? Because it provides good response time, less waiting time. What about the background? Background, we need some good throughput, such as the first come, first serve. Once it is selected, it should be completed. So we can allocate, we can use different scheduling algorithm for each queue. Then problem is, yes,
How to calculate the waiting time of our algorithm?
it's the same thing.
Same thing.
Yeah. So for example, in this case, the arrival time is a 0, right? So waiting time is a process 1 waiting time is this amount is 57 plus this amount of time, okay? That is the process 1 waiting time. Process 2 is 20 plus, it's done, 20. Process 3, then add up, sum up, then divide by 4. That is the waiting time. Okay, it's the same thing. Okay, so we can have the multi-level queue, different queue in the waiting queue, okay? Depending on the type of process and assign the different scheduling algorithm. Sometimes it's more the various like the system process, interactive process, whatever. Okay, then apply the different queue. Then what will be the problem when you implement such a multi-level queue? You need to implement scheduling of queue because you have only one CPU time. Anyway, it's not possible to run 2 queues at the same time. So for example, 50-50 or round robin. So 20, 20, 20, 20. Within 20, you can apply scheduling algorithm of this queue. Within 20 time, you can apply the scheduling of first come, first serve. So you need to consider the scheduling of the along the queue in multi-level queue. So in this case, for example, you can give the 80% to the round robin, the foreground queue, and 20% for the background queue, which means 8 times log, then 2 times log. 8 times log or 2 times. Or you can do the 4-1-4-1 instructive, but on average, 80% goes 80% of the CPU goes to the foreground, and 20% goes to the background. Something like that. Or sometimes you can apply the priority-based approach for the scheduling of the queue. So this one is the highest priority, this one is the lower priority, which means if there is a process in foreground, it should be processed first. Then once it's empty, go to the next one. And if you have another level, you can do the same thing. So you can implement, you need to implement another scheduler among the queue. Then, one of the problem of this one is if you implement the priority-based approach for along the queue. Anyway, so you need to implement the scheduling for this one, along the queue. So it takes a time. It's an overhead. Okay. Also, if you are using the priority-based approach, so sometimes you may get the starvation problem. Okay. So to address this one from the multi-level queue. So this is, for example, round robin with a time quantum 1. This is a round robin time quantum 2. Then first come, first serve. So if the process will enter the first queue always. Okay, you do not classify. But this one instead is then if with the round robin 1 with the time quantum 1 is a process, then terminate. Otherwise, go to the next queue with the round robin 2. If that is completed, then terminate. Otherwise, go to the next one. Eventually, it will be processed by first come, first serve, last queue. So output of the one queue will be input of the next level queue. Then you can address the problem of scheduling. Right? You don't have to schedule this one. Just enter this, then next. Also, you can address the problem of the priority base. Okay, this is called multi-level feedback queue. Queue scheduling algorithm. So this is the algorithm that you need to implement in your first project. Okay? As a simulator, just like you have seen before. So you need to implement such a simulator. So multi-level feedback queue, we will see a little bit more details of it. So for example, we have the 3 queues over here. So this is a ready queue. How many CPU processors we have? Only one. Okay. When we have the multiple, we can actually assign the process to the different scheduler. Okay. Then we can get the scalability. But unfortunately, we have the one CPU. So then first we will assign the different scheduling algorithm for each. You do better, use fast response time, the algorithm first. Okay? So which means, for example, quantum round robin with a quantum small quantum, 8. Then next, if that is not enough, which means it's longer job, it's the bigger CPU burst time process. Then we'll go to the next. It has a little bit longer quantum size. If that is completed, it's okay, terminate. Otherwise, in the first come, first serve, eventually it will be completed. Okay? It has a good throughput. So if a process has a big amount of CPU burst time, it will went to up to this one. Another problem of this one is this algorithm is you can use also different the priority along the queue. Okay, so you can give the fixed amount of the CPU time at the 20, 60, or 30, 30, 40, or you can allocate the priority. This is a higher priority than this. Which means if there's any process here, you need to process this one first. So in your project, you will use such a priority-based scheduling along the queue. Okay? So I will give the one example of this one. It's a very flexible. Okay? The problem is, so little bit more complex than other CPU scheduling algorithms. Why the complexity is important in operating system? CPU scheduler, it should be very, very busy, right? How many processors you have? There are a bunch of processors running on the operating system. Also, you need to, very in short period of time, you need to decide the next one, every certain period of time. So if that is complex, then it will be overhead over here. So, this is your project you need to implement. In your project, first, program language, you can use any program language. But when you submit your project, the GA and me will grade, but GA may not know all the program languages, which means if we are using, for example, the certain ID or library, you need to include everything. It's also a good idea to submit the executable file. You compile and executable file or install file with your source code also. Okay? So if GA cannot compile by following your instruction, it's automatically fail. Okay? It's not his responsibility. You need to think he doesn't know anything about your program language. Okay? So you need to provide the details of the instruction or require the system file or even programming. He may not have your programming language. For example, .NET he does not have, so you need to provide all the information. Okay? So also good idea, if he cannot grade, he will ask the second chance to demonstrate your program. Okay, so you can use any program language, but should be compilable and executable. Okay, when he grade. Then the requirement is that we are going to implement 3 levels of the multi-level feedback queue. First one is a quantum time slot A. So it's also a good idea to specify what is the one time unit. It can be 1 second, it can be millisecond. Millisecond is too short. Okay? Think about the reasonable period time amount. But 1 second is too long usually. Okay? Which means to complete if you have the 100 CPU burst time, so it will take at least 1 minute and 40 seconds. So you need to think about the reasonable, the time, real time slot for the time unit. So anyway, 8 time unit time slot, and the next one is a round robin with a 16 time slot, and last one is the first come first serve. So you are going to implement such a priority based multi-level feedback queue, which means if there is any process in the first level, the CPU will be used for this one. Once completed, the next one. Why? This one is the process. There is an incoming process. This one should be processed. Okay, because it's a priority. Okay. The other rule will follow the same as in the lecture slide. Okay, so it's a priority based queue scheduling. So Q0 is the highest priority, then Q1 followed by Q2. Also, if a new process coming in Q0, and we'll get the 8, right? Even though it's being processed by the other queue, the new process is coming in the new, first one, that is the highest priority. If not, finish next level and next level, okay? Also, you need to implement the PCB data structure. It can be, for example, if you are using Java, it can be object, okay? So you need to manage the process state by PCB structure. So GA will check whether you implement the PCB structure. In your PCB, you need to keep not all process is a simulator, only this is a requirement, the process ID, arrival time, actual execution time, and queue number, where is current queue number, Q0, Q1, Q2, something like that. And also, if you need it, you can add more. Definitely, you need more information. Okay? This is not the data structure in your memory. You can use your construct or the object or some data structure that you have. You can use depending on your programming language. Okay. What about the process state? I do not provide it, but the GA will use his own for testing. Okay. You can create by yourself, randomly create more than 20. So it's also a good idea. Instead of random, first, while you are implementing the MLFQ, you can have the certain fixed, the process state and the CPU burst time. Okay, more than 20. Then test the test. Once it is completed and correct, then you can test with a random creating. Minimum 20. So this is the example. Simulator of the simulator using the PPT file. So we create such a 10 processes, but you need to create them more than 20. Okay, with the arrival time and CPU burst time. Yes.
That is kind of simulator, not real process.
Oh no, this is a PPT file. So you will implement simulator.
Simulator. That's
Okay.
simulator.
Yes.
Okay.
I will show you one of the example that is implemented by others. Okay. So process 0 coming in. Okay. CPU burst time is 10. There's no other process. Okay. The T2 means it's a time 2, current time. Okay. So also P1. So why don't you take a look at this part? So P0 take the first times 8. Okay. Then P0 coming in at time 8. Okay. Then is the process 0 completed? No. It has a 10 CPU burst time, but only two remain. So move to the next level. However, it cannot get the CPU resource. Why? The Q1 is a lower priority than Q0. Q0 has the two process. You will learn round robin with the time quantum A for the Q0. So P1 is terminated. Then terminate is gone. Then P2 move to the next level. So we do not have the process in Q0. Then Q1 will run with round robin with the time quantum 16. Then P0 is terminated. It's done. And you need to manage this one also for visualization. That's also a good idea. Okay, and so on. So let's see Q2 case. Yes. Finally, P5 is not completed yet. It still needs 4 CPU time. Yeah, but it cannot get until Q0 and Q1 is empty. Okay. Then finally, they are done. Okay. Then one more thing. You need to analyze the data, which means what is the waiting time and what is the turnaround time, what is the response time on average. Okay, I didn't do this one, but I will show you another example of this program is one of the examples, but it doesn't implement multi-level feedback queue. It's a simple, the first come first serve, and shortest job, and shortest remain job, and round robin. Yes.
What is the turnaround time?
Turnaround time is the time when you it's between when you submit the process is arrival time and to the complete time, terminated time. That includes CPU time and waiting time, everything. Okay. So this is the example of the simple CPU, but I will show you. Okay, but this one also consider I/O weight, so it's more complicated. So you don't have to follow this one. This is just the example of that. Okay, so this one has also consider I/O weight. So far we didn't consider any I/O weight here, but in real the scheduler definitely need to consider such a I/O weight. If we run, it's already done. So then this is the example of the report for the response time, waiting time, and turnaround time. But if we wanna see in this multi-level feedback queue, we have the 4 queue with the time quantum 3, 4, 5. The last one is a P4. Rest means it's a 1 by 1. So time CPU, we have in this case, there are 5 processes. Okay, 5 processes. There are 2 types of the process. One is a regular program and background, and arrival time and CPU burst time they need. The reason why it's a 5, 5, 5 is between the 5 there is a I/O wait. So that is a more complicated one. But the reason why I show you is just idea how you can implement this one.
But in our project, CPU burst time will be one number, not multiple numbers.
Oh no. So we do not consider, and it's the total amount of time that you need. Okay. Then it's next the I/O. Go to the I/O. Then you can see the message at time 7 no process in the CPU because A is processing but it's in the wait queue. So that is the reason there is no CPU over there. Then process B is coming, we'll get the Q1, first Q1. Then process A is returned and also C is executed and B is get the 3, the CPU time, but C is get CPU burst time because it's a round robin by 3, okay, in the first queue, and so on. So this is the, you can see that this one shows the queue, each queue status of the each queue. And finally it's done. Then shows the such a CPU utilization is 91%, okay? And overall turnaround time is a 57. It's average. Any question? Yes.
So when the program start, it will create real process or that it just
Oh no, it's not a real process, it's a simulator.
it's a simulator.
Okay, yes.
It's not depend on any process
No.
anymore.
No. Okay. It's only by your programming
Yeah,
algorithm.
And
So we are going to focus on only the algorithm. Okay.
and here we will appear we'll show you the idea. What's the meaning of the idea? How to track the idea?
Idea means the idea of the
Of the
algorithm.
Yeah.
Yes, you implement the MLFQ algorithm only with the given condition. So condition is you have 3 Q. One is the round robin with the time quantum 8. Next one is the time quantum 16. And the last one is a first come first serve. So along the queue we are going to use priority based. Q0 is a higher priority than the Q1, then Q2. Okay? Yes.
What about the input data?
Input data you can create by yourself.
By
Then
yourself.
when GA grade, he will use the same whether your implementation is correct or not.
I can put any arrival time. I can
Sure.
put, you know,
But if your algorithm is correct, no matter what input
What
data,
input
it should be correct, right? Any other question?
in this example, can I change from the interface the arrival time? This program.
In this program,
For example, is A is arrival time is 2. Can I change it to? Can we change it?
to do that, we
Yeah.
need to
Or
Use
the
user
outsource?
input. I do not test this program a lot. I just found from internet. So choose the demo file or the customer info file, input data. You can, here, we can change. Here.
This is where it's very complicated.
Yeah, this one is more complicated because it need to consider I/O weight also. So your implementation much easier. It looks like the PPT. their brother. Okay.
So in that multi-level, we don't have to consider the starving algorithm for each queue, right?
Starvation, no. Eventually you will get. Why? Because you have the not infinite the process. You have the limited process. So 20, 30, 40, it will be ended eventually. So you don't have to worry about the starvation. Okay, so the most important thing is the program language and the environment. If you are using the general, the well-known the program language like the .NET or the C++, it's probably okay because everybody has the program environment or ID. Eclipse is also fine, and the Java, pure Java is also fine. But sometimes there exists the student who use the very rarely use the program. Okay, it's okay. So because it's not a programming contest, okay? So I'm going to see whether you implement the algorithm correctly or not. So, but in case you are using not well-known program, especially GME, I'm not familiar with that, you need to provide all the information, okay? Any system library, anything, and details of readme file instruction. That's it. So we will move to the next topic. Today also, I'd like to end the class 12 and noon. Yes.
Each process has different way to calculate the average waiting of the.
So calculating the waiting time, turnaround time is we already discussed. You can just follow that idea. Okay, what is the response time? Response time is the between arrival time and first execution time, executed time. So you can sum up such a amount of time and divide by number of process, that is the average waiting time. And turnaround time is the same. And regarding to graphical user interface, you don't have to follow the GUI that I show you, so you can be creative. At least you should have such a reporting after execution. It should show the average waiting time, average turnaround time, average response time. Did I post this page, PPT5? Can you find this from the canvas? No? I will, if not, I will upload this file for your understanding. Basically, the thread is the same idea as the process, the scheduling. The different thing is, why don't we go back to the chapter 4, the thread management. During the thread management, there are two types of the thread. One is kernel thread, another one is user thread. So depending on the types of the user thread and kernel thread, there is a one to many, many to one, or many to many. So in case of many, you need to scheduling, which the thread will be selected. Okay. So that is the process contention stuff. It's basically the same idea as the process. Okay, then next one is a multiple processor. When we have the multiple, the processor multi-core, we can include the multi-core. And so when we have the multiple processor scheduling, it's more complex than the single processor. Okay, there are different types of the multiple processor. One is the SMP. SMP is you have the exactly same, okay, CPU, a number of CPU, they share the memory. That is a SMP, symmetric multiple processor. Another one is asymmetric multiple processing. In case of the asymmetric multiple processing, they are different, so they cannot share any information. Each processor should have their own scheduler. So even that is simpler. But nowadays, most of the as the multiple processor is the SMP machine, the asymmetric multiple processor. So at that time, we can consider affinity. Affinity means when we have the scheduler needs to assign each processor even. Okay, when you have the ready queue from the ready queue. In case of asymmetric, this CPU is different from this one. So each one should have the scheduler. So it's not a big problem. Problem is when you have the symmetric. So this processor can be anything. So you need to assign which processor will be used for the specific process. The problem is whether we can allocate the specific process to the specific CPU. So that is called the affinity. The affinity, you'd better allocate, assign the process P1 is always 0. Why? Because P0 know about this process. It will be reused. Not all the data in the register will be clear, empty. So if you can reuse the same processor, you can reduce the time of latency, dispatch latency, the context switching time. So at that time, not always you can use the dedicated processor for the process. So if you'd like to use the same processor for the specific process, you try. That is a software affinity. Okay? But if this processor is being used, you can use a different one for the process. It's a software affinity. On the other hand, hard affinity is this processor should always use the same CPU processor. What if this CPU is being used by the other process? You need to wait. Okay? That is hard affinity. You need to consider such a processor affinity for speed. Also, in case of the multiple processor, definitely you need to consider balancing of the CPU load in your scheduler. Okay? So there are two types of the migration, which means whether this CPU is idle at that time, this one is push the information to the other processor. I'm available, so why don't you? Or so you can get the pull the information about this one. I'm very busy, so pull the information about other processor. Then if they are available, then migrate the process affinity to other. So multi-core basically is the same idea as the multi-processor case, but it's faster and consumes less power because all the thread, the core is in the same chip. Okay. So nowadays multi-core processor is in general. The next nowadays very important issues of the scheduling is real time. The CPU scheduling. What does that mean? Real-time CPU scheduling. Real-time. When probably you use a lot the real-time processing, real-time something. What does that mean? Real-time. Is it fast?
It's not comparing to anything.
It's not comparing to anything. What does it mean when you are saying the real-time process, real-time application, real-time machine, real-time? So fast, usually fast, but not always fast. So think about the nuclear plant the disaster. So once the tsunami or something, the typhoon hit the nuclear plant, you should alarm within what? Given time, as soon as possible, but it's not easy. Computer understand what is as soon as possible. Fast, what is a fast? Even though it's a millisecond, there might be faster than the millisecond. So real time is a very important. So somebody need to decide within 5 seconds or within 1 minute. Once the tsunami hit the nuclear plant, within 1 minute should inform to the fire station or the government office and all the people. So within 1 minute. So within one, if the such an event is informed within 1 minute, then the other people can be prepared. So that is the policy. Then real time means within 1 minute, your device should work, no matter what situation. So real time CPU scheduling is needed at the time in critical